We examine in this paper gesture input with devices designed to be worn on the upper body, such as smartwatches, rings, and glasses. Our investigation is motivated by the fact that wearables are surpassing smartphones as today's fastest growing technological innovation for mobile users. However, gesture-based interactions with off-the-shelf wearables are based on certain assumptions about their users' motor abilities. For example, a smart ring assumes the motor ability to move the wearing finger, rotate the wrist, make a hand pose, and possibly raise the forearm in the process. Upper body motor impairments cause challenges during input with upper body wearables implementing such assumptions. In this picture, a person with spinal cord injury controls a smart ring with movements of the arm, not the fingers. To understand the gesture input articulation performance of users with upper body motor impairments with upper body wearables, we conducted a controlled experiment with a device worn on the wrist as a smartwatch, on the finger as a ring, and on the head in the form of a pair of glasses. Our experiment involved 14 people with various types of upper body motor impairments, as well as a control group of 14 people without impairments. We had two within subjects independent variables: wearable, nominal variable with three conditions, watch, ring, and glasses, representing devices worn on the wrist, finger, and head, and modality, nominal variable with two conditions, stroke gestures performed on the wearable device and motion gestures of the body part wearing the device. Stroke gestures are paths produced on a touchscreen for which symbolic associations are created with system functions, such as the letter M stands for menu. We designed a set of 12 stroke gestures for input on the watch, ring, and glasses. We selected the gestures to balance a number of criteria, such as the number of strokes, the complexity of the geometric shape of the gesture, and others. Motion gestures are movements of a body part, such as moving the finger wearing a smart ring. We designed 3 gesture sets for the finger, wrist, and head, corresponding to the 3 conditions of the wearable independent variable, by drawing from prior work on motion gesture input with wearables and existing taxonomies for motion gestures. We used the Samsung Gear Fit 2 to collect gestures in the smartwatch condition. To make sure that gestures were collected with the same resolution across the glasses and the ring conditions, we repurposed the Gear Fit device, which we detached from its strap and affixed with a 3D printed support to a pair of glasses and to a ring form factor respectively. We collected more than 7,000 stroke gestures and nearly 4,000 motion gestures from our participants. The completion rate of the experiment for the participants with upper body motor impairments was above 90%. We found that stroke gestures produced by users with upper body motor impairments on wearable touchscreens at various locations on the upper body were longer, wavier, less consistent, with more strokes, and took twice as much time to articulate compared to the same gesture types produced by the control group. Also, stroke gesture articulation performance was influenced by the location of the wearable. Stroke gestures in the watch condition were the fastest and had the highest geometric consistency. Unlike stroke gestures, we found that motion gestures are produced equally fast and with similar kinematic characteristics by both the participants with and without motor impairments. The location of the wearable did affect gesture articulation, but in a similar way in both groups. Motion gestures performed with the finger and wrist were faster than head gestures, but also less consistent. Based on our findings, we propose implications for more accessible gesture input for upper body wearables by capitalizing on the principles of ability-based design. The ability-based design approach emphasizes the importance of focusing on users' abilities in context based on 7 principles. In our case, abilities refer to gross and fine motor skills of the finger, wrist, arm, and neck to perform stroke gestures and motion gestures on and with rings, watches, and glasses. Next, we discuss some of the implications of our findings. The ability principle states that designers focus on users' abilities in a given context. Our findings suggest designing gesture sets that include both stroke gestures and motion gestures according to the motor ability of the user to move fingers, land the finger on a device, maintain stable contact with the device, rotate the wrist, produce accelerated movement, raise the hand, and control cervical muscles. For example, participant 14 from our experiment was not able to perform stroke gestures on the ring but was able to move the finger wearing the ring. Another implication of the ability principle is to design customizable devices in terms of the location on the body where they are worn to enable comfortable reaching for stroke gesture input, but also motion gesture input with less effort involving that part of the body. An example is participant 7 from our experiment that could not raise their hand to perform stroke gestures on the temple of the glasses, but was able to use the same type of gestures when the sensor was worn in the form of a watch and the ring, respectively. The availability principle states that designers use affordable and available software and hardware. Since smartwatches and fitness trackers are becoming mainstream, requirements regarding their affordability and availability are implicitly met. However, other wearables such as rings and glasses are still on their way to mass adoption. A practical solution to affordability and availability is to reuse the touchscreen of a smartwatch, a prevalent device, and affix it to various parts of the body for easier and more convenient access with the finger during touch input, but also for instrumenting those body parts for motion input. The performance principle means that systems employ data about users' performance for best match of abilities. The implication in our case is to model users' gesture articulation behavior. Aspects such as the amount of time to articulate a gesture, the number of strokes produced to draw the geometric shape of a stroke gesture, and the axis of movement along which motion gestures are articulated are examples of information that the wearable device could collect and use to tune accessibility settings, such as how long to wait for a multi-stroke gesture to be entered before calling the gesture recognizer. Overall, we provide 10 practical implications informed by our empirical findings to implement the 7 principles of ability-based design towards more accessible gesture input with upper body wearables. Please see the discussion section from our paper for more details and examples. To enable future work in this direction, we release our 2 datasets composed of nearly 11,000 stroke gestures and motion gestures collected from 28 participants. The datasets are freely available for research purposes, and they come with C# source code that computes the measure reported in our paper. Thank you for watching, and please see our paper for more information.